Hello, everyone. We have an exciting prototype to share with you today. But our prototype is laboratory-grade computer science. It is not safe to give software of this nature a live demonstration. Listen carefully while I outline the 3 safety precautions of this academic computer science presentation. Number 1. For safety, Alex Warth will do all of the demos live.
Alex Warth, everybody.
Number 2. For safety, Marcel Goethals will blend in with the audience. And number 3. For safety, Ivan Reese, me, will be pre-recorded. And Ivan Reese, me, will wear high-visibility flagging tape. What? I put it in your backpack for safety. Today, we are excited to present Inkling. We work at Ink&Switch. We work on ink. We want a notebook. A notebook is a book, one of the technologies of all time. A notebook is blank. You may fill it with your own ideas. It is a physical space, one page after another, a structure that gives shape to your thoughts, tactile, malleable. But you also love the computer. I don't need to tell this room of people why you love the computer. Nobody loves the computer as much as the people in this room. But the computer forces your thoughts through an aperture, the breadth of a mouse cursor, tapping buttons one by one. That is not how we want to feel when we are thinking, because feeling is reality. We want tools that we can wrap our hands around, ones that let us scribble and sketch. We want a dynamic notebook. In Inkling, the pen draws. Erase by pressing 2 fingers to the screen whilst drawing. Draw another ink stroke, then tap the ink splat in the corner to enter meta mode. Tap the ink stroke to add handles. In meta mode, drawing creates a gizmo, 2 connected handles with a special sigil at the center. Handles want to snap together. Tap the sigil to impose a length constraint. Tap again to constrain both length and angle. And once more to constrain just the angle. Draw a second gizmo, and then draw a wire to connect their sigils, making their lengths and angles equal. Now draw a wire into the nothingness, and 2 properties appear, each of which can produce a numeric value. Tickle the value with your finger, and the gizmo reacts. Some numbers are light and free to change. Other numbers are dark and must keep the value you give them. Tapping a number toggles this behavior, and every connected gizmo and number changes in kind. and from the nothingness tap the pen to create a linear equation, a simple tool for powerful mathematic manipulation. Math, wires, gizmos, handles, and ink. We started by drawing ink strokes, then drawing constraining gizmos onto those strokes, and drawing mathematical relationships for those constraints. Inkling has a smooth progression from doodling to modeling. At every step, you have something useful and playful. The focus on physicality and drawing means you often make a thing just by feeling your way through the possibility space. The tool doesn't work at the speed of thought because you're not even thinking. You're just feeling. It's faster. Feeling is reality. And Inkling doesn't feel like anything. Here's how we achieved that feeling.
So everything you see in the system is either represented as variables or constraints. And when you mess around with stuff with your fingers, what we're doing is we're using the gradient descent solver to pick new values for the variables to make the constraints happy again. And so, but it's not trivial to create this kind of feeling that the material feeling that we have in Inkling. And so I'm going to talk about 3 of the techniques that we use in the system to make this work. One of them we call propagation of knowns. And so, thank you. I'm going to illustrate this with a little example. Hang on. So, consider this little construction of 2 gizmos that are both angle and length locked. And what happens when I put my finger here on this handle and move it around. So, normally with constraint solving, you'd be doing all kinds of stuff. But here, we're doing something much simpler. What's going on is that when I put my finger on this handle in the bottom, the system knows that I want it to be right there, right? And because the position of the second handle is fully determined by the position of that finger that's down, I'm not even using constraint solving at all. Same thing goes for the third handle. This is a kind of data flow, but you can actually use it from any direction, right? So right now, the positions of the 2 handles on the outside are being determined by the position of the handle in the middle, so on and so forth. Okay, another neat idea that we use here is something that we call unification of variables, and that is to say that we don't use equality as a constraint. And so here's an example to illustrate that. I have 2 gizmos, and I'm going to pull out their angles and lengths. Let's put the angles together and the lengths together here, and show you the values. Okay, so right now if I just manipulate these gizmos, you see that the values of the lengths and angles are completely independent from each other. But let's see what happens when I snap these handles together. What you're seeing here is 2 overlapping gizmos. That's why you have this arrow going on both sides. And the interesting thing that's happening is that their length variables and angle variables have been unified together to reduce the number of dimensions that the solver has to worry about. And so now if I scrub the length of one of them, you can see that I'm actually scrubbing the other length because that's the same variable. The same thing is happening with the angle, even though they're 180 degrees apart. This is like just a different kind of equality. All right. Yet another idea that we're employing here is what we call clustering. It's similar to what people in the video game industry do. Yeah, with simulation islands in their physics engines. So here I have 2 chains of gizmos that I can manipulate independently, and because these constraints and the variables have no overlap with each other, we can actually hand them off to the solver to solve separately, which improves the efficiency of the thing and also enables the solver to converge on a solution that it sometimes would otherwise not be able to converge on.
Feeling is reality, and Inkling doesn't feel like anything. Here's how we achieved that feeling.
So one of the things we were thinking a lot about at the beginning of this project is user interfaces for drawing. So there's a couple of ways that that thinking sort of manifests in this project. I'm going to really quickly talk about them. Some of the things we wanted are like an app that you could use with both hands all the time, all fingers, all over the screen. You could have multiple pens going on the screen or multiple people sitting around the same iPad all playing. And so the way that we designed the interface is that, oh shoot, what was the thing? Yeah, so the constraints and the interface have this like interplay between them, right? So if I have this gizmo, do you want to go to a, you don't have to show it.
Yeah, I could show a gizmo.
Yeah, if you have a gizmo with a locked length and you put your finger on one end and pull, the gizmo's gonna go with your finger. But what happens if you put your finger on both ends and pull them apart? What should happen? Should the gizmo kind of go in the middle and keep its length or stick with one finger or the other? We think the only thing that makes sense in this case is that the gizmo should obey the fingers because that's the input that you're giving it. So that preservation of user intent is really big. Another thing that was really important for the design is that we don't have any absolute coordinates. There's no X, Y positions. You never see that kind of stuff. We have numbers for lengths and angles, and lengths are good because they feel kind of relative and you can build your own coordinate spaces out of that. But angles suck because there's an absolute 0 degree pointing to the right. And you could use, you know, a linear equation to try and change that frame of reference angle, but that doesn't feel very good. And I asked Ivan what he would do about that. And do you know what he told me? Do you know what Ivan told me? He told me, algebra is an illusion of the mind's eye. Did you just tell me to go F myself? So yeah, this is something we hope to explore more in future work. And yeah.
Here are some further explorations that Inkling has encouraged us to take. With a handle that leaves a trail of ink, you could visualize the motion of your models. You could take one of those handles and make it go everywhere within the range allowed by its constraints to produce elaborate curves or even filled regions. What we built is but a prototype of a constraint solver and a user interface. Yes, this prototype is not the notebook we seek. There are no pages in sequence, no book-like structure for your thoughts. But what Inkling gives us is better than thinking. Inkling gave us a feeling. It is our new reality. We have all been changed by it. All the technology we created is in support of that feeling. Feeling is reality.
Yeah, so if you want to play with Inkling, there's a GitHub repo. You can download it on your computer.
Nobody loves the computer as much as the people in this room. But the computer is not the point. The code is not the point. The point is how this feels. Feeling is reality. Feeling is reality. Feeling is feeling is reality. Is feeling is reality. Is reality. Is reality.